Hello everyone, I'm Petter Holme from Tokyo Institute of Technology. So I'm very happy to talk here, and thanks to the organizers for inviting me. And to start, I would like to say that I'm a physicist by training and from a little bit of a different background. I've been studying temporal networks since 2005 and I really enjoy the topic, but I usually have been studying it from a different perspective than most of you. But that much said, I really enjoy algorithm design and the kind of problems involved in doing that. I really think it's a lot of fun. On the other hand, I'm a bit of an amateur. So what we see in the background is visualization of the interaction among French primary school students age 6 through 12. So it's from the socio-pattern study that maybe many of you know about. So they put RFID tags, RFID sensors on the school kids and recorded the interaction. So one link here represents the two kids who have been in face-to-face contacts within 1.5 meters. And the blobs, they are the different classes, and the squares are the teachers. Now this type of visualization can give you some kind of like feeling for the complexity and the structure of a temporal network, but it's not so good for reasoning about things like algorithms or even like processes on top of the temporal network. So instead, the kind of typical input data that we get is what we see to the left in this figure. It's the like 3 columns where every row represents what I call a contact, sometimes it's called an event, between 2 nodes at a given time. So time is discretized. And a typical visual representation of this that kind of contains all the information is seen to the right. So here every line is a person, and the vertical connections shows the contacts between pairs of persons at the different times. Now my talk will be about the SIR model and in general about disease spreading on modeling on top of temporal networks. So I assume that we have this kind of temporal network given from observation like this French school data, and on top of that we are running disease simulations. And how to run these disease simulations, the detailed definition of the model, it's kind of well accepted in the field of network epidemiology. So we assume that there is a constant infection rate, so the contagion process across a link between a susceptible and infectious is a Poisson process throughout the duration of this link being SI. And then we assume a constant recovery rate, giving exponentially distributed durations of infection. And typically we assume that there is only one seed node of these epidemics. And as for algorithms, for this SIR on static graphs, there is the Gillespie algorithm. That's the kind of like traditional way of simulating this. There are a few faster, more modern algorithms like the event-driven model that's called the next reaction model in the context of chemical modeling, and maybe the fastest is the composition rejection algorithm by Saint-Onge and collaborators. So now we reach the problem that we have the SIR model on this kind of temporal graph of like contacts, like imagine the French school kids again. But when you think about how to design SIR model on temporal networks, you soon realize that there are many kind of small choices you have to make to come up with like a detailed simulation algorithm. So to do that, we have a few design principles here. So first of all, we want the model to be realistic. So after all, the goal is to simulate reality. Then we want we want continuity. We want to be able to, if we project out the time dimension, we should kind of retrieve the SIR model on the static graphs. And we want it to be simple, so we can reason about cause and effect easily. And primarily, we want it to have the same level of abstraction throughout the modeling. So not like kind of one component of this model is kind of much less realistic than another. We want it to be generalizable so that we can go from SIR to SEIR, for example, like in the model COVID. If all of this above design principles are kind of undecided, as a final tiebreaker, we want the algorithm to be as fast as possible. And you can read about this kind of consideration in the paper that I quote below. So to get to this kind of like more algorithmic formulation of the model, we initialize the nodes by making them all susceptible, and then, as mentioned before, we pick one node as a seed, and we pick time in the time interval, like throughout the sampling time of our data, as the first infection time. And this is a little bit tricky because imagine that this time is at the very end of the data, then the outbreaks will of course be relatively small. You could argue that you should choose this kind of in the beginning, but then the choice becomes less random and more dependent on the kind of short-term structure in the data. So I think the only way of doing it in a principled way, without kind of taking specific consideration to the particular data you have, is to choose it with uniform probability between the beginning and the end of the sampling time. And then for recovery, we stick to the SIR model on static graphs and assume exponentially distributed times. And for the contagion, we assume that every event or every contact recorded in our data has the same chance of spreading the disease if the contact is between an S and I. The straightforward way of doing this, the straightforward algorithm, is just to go through all the contacts in the order of when they happen. And if there is a contact between susceptible and infectious, you spread the disease with a probability beta. And whenever a node gets infected, you draw the time to recovery from an exponential distribution, and then you can break the simulation when there are no more infectious nodes. There are some ways to speed up this algorithm. For example, remember that the infection can kind of enter the contact, the temporal networks, in the middle of the sampling period. So you can use bisection search to find the first contact that can potentially spread the disease. And of course you can stop the simulations when there are no more active infected nodes. But there are a bit smarter ways of faster algorithms to do that, and this is my contribution. So in a way, the ideas are already in the literature for static networks, so it's not kind of a fundamentally different contribution to the field of algorithms for compartmental models on temporal networks. But anyway, I think it's a bit nice. So the fundamental idea of this event-based algorithm is to focus on like individual infection events and the subsequent events that they create. So every time someone is infected, that generates a possible future infection events. So you generate kind of candidate events, future events, and put them on a priority list, a binary heap in our case. And the other data structures we use are shown in B here. So we represent the contacts through an adjacency list. And this adjacency list is sorted in order of decreasing last time of the contacts between two nodes. Now one subroutine of this algorithm, I call it contagious contact, is performing the task to find which one of the contacts in an adjacency list that could potentially spread the disease. So imagine if you look at in the bottom of the screen at this contact list. So first the contacts between A and C. Now assume that A get infected at time 3. So 2 is out. I mean, C cannot be infected by the contact at 2 because it already happened. It can be infected at 15 and 19. So which one of these? So this subroutine first uses bisection search to find this kind of smallest index where the infection can happen, and then among the remaining contacts you draw a random number, given that this is actually a Bernoulli process with a probability beta. So you can see at step 2 you use this transformation of uniform random numbers to get the index that could potentially spread the disease. And then you have to check if there is no event that would infect this node earlier already on the heap. If there is no such event, then you put this event on the heap, or you update the event that is potentially there with a later infection time. Now the next subroutine that I will discuss, I call it infect, handles the infection event of one node I. So essentially, you pop the individual I from the heap with the earliest infection time. Then you go through all the neighbors j of I, and you call this subroutine contagious contact to get the contact that would spread the disease. And if there is no such event already on the heap that would infect this new node, and if the recovery time of the node is kind of not earlier than the time you get from this contagious contact, then you put it on the heap if it doesn't exist there, or if it exists you update the contact on the heap. And you might remember that to keep a heap balance there are two operations. It's called heap up and heap down, and the heap up is essentially much faster. Both are logarithm of the height of the heap, or no, logarithm of the number of nodes in the heap. But heap up is essentially only just a few operations, while heap down is a bit more complicated. And here in this routine we can use only heap up, because we know that the time of the node that we update is earlier than the time in the heap already. So the overall this event-based algorithm, it reads like this, that we first of course we read in the data, we infect the source node, and then while there are any nodes left on the heap, meaning that when there are some infected node in the system, we call this infect, and we continue until the heap is empty. So this is a kind of example output. Now in a static SIR model, the SIR model kind of reduces to a one parameter model essentially, but in temporal networks it doesn't. So it's a two-dimensional parameter space where we have the transmission probability on the x-axis and recovery rate on the y-axis, and the biggest outbreaks color-coded here. They are in the region of like high transmission probability and small recovery rates. Now we validate the program. I mean, this is a bit silly maybe to show, but we do it primarily by comparing to analytical results, which you can get. We have some other paper about how to use computational algebra to get the exact expression for the outbreak size. But it's only feasible for small graphs, because essentially they become like very high order polynomials, one polynomial divided by another. And we choose this particular network because it's unusually complicated, and it's kind of fun. I recommend you to read more about it. You can do that on a paper to the left. Now the time complexity of this event-based algorithm is, you can see it here, it's L, where L is the number of edges, times log n, times log c, where c is the number of contacts, n is the number of nodes, compared to the straightforward algorithm, which is m plus c. So you can see that when c is large enough, which is kind of a typical case, then this logarithm kicks in and makes the event-driven algorithm faster. So this figure shows the performance of the event-driven model relative to the straightforward model for some model network. And of course, from the previous slide, you know that if you just put the ratios right, then you can get a kind of arbitrary speed up. But this also shows that in practical situation, it is much faster. This is also showing the speed up for one of these sociopatterns dataset. I think it's not the French school kids, but it's a similar dataset. And throughout this figure, like the speed up is always larger than 0. So meaning that the event-based model is always faster. For a large part of the parameter space, it's not that much faster, but typically when the recovery rate is low and the transmission probability is low, meaning that there is there are only a few sick individuals lingering in the population, and a lot of the contacts are actually between S and S. So they are not kind of the straightforward algorithm would keep them, would count them, but this event-based algorithm would not. Then that's when the speed up is the largest. And this is showing the speed up for many different data sets with a fixed parameter. So essentially the event-based algorithm makes things much faster in a few cases and a little bit faster in many, but never, it's never slower. It could in principle be slower, but for practical use I haven't found such an example. So next I want to share a kind of ongoing project, and you are welcome to join if you can help me out. So now this is about the SR model with fixed infection duration, so not the exponential duration of the infection time. So this is a setup that's been used sometimes in the literature. It kind of violates what I said before, that we should have continuity to the traditional SIR model and static graphs. But anyway, what I think we can gain here is that for different durations t, we can kind of do them all at once. Instead of calculating for every duration, we calculate the outbreak size. We can instead for every single node calculate the time required for the disease to reach this node from a given seed node. So I should have had a even nicer illustration of this. Okay, but my naive algorithm idea here is that we have, like, for every node given a seed node, we have a variable representing the minimum value of time needed for the disease to reach this node. And then we kind of go through all the contacts and update this variable xi, so that for every contact, we reset xi to the maximum value of what it already has and what the neighbor node has plus the time since the neighbor node was infected. So this is kind of inspired by the Floyd-Wilkinson algorithm for shortest path, and unfortunately it doesn't work. And the reason it doesn't work is that there are some kind of almost contradictory examples, and normally you would assume that if the infection time is longer, then the disease should spread further. But if we look in this figure, in the top figure, it could be that if the infection time is longer, then the disease reaches some kind of critical node earlier, so that node gets infected but also recovers earlier. And when it recovers, it is in the R state at the time when it would really have been needed for the disease to spread to a large part of the network. Now I realized that you can find this kind of exceptions, but then there could be exceptions to the exceptions. And I didn't yet figure out how you can do this recursively to find exceptions to exceptions to exceptions and include that in a kind of fast algorithm to calculate all of that. But I think this would be an interesting research problem. It's also like, if you don't consider these exceptions, you have a very fast heuristic. And I think it's kind of fundamentally interesting how often these exceptions actually happen. So with that, I say thank you and see you again.